Have you ever wondered how we know how far it is to distant objects in space, to other stars, solar systems, and galaxies? After all, you can't go out there with a ruler and measure. It turns out that there are a lot of different methods and different approaches are used depending on the distance to the object in question. The reason I raise this question isn't because we need to know these distances in order to evaluate models of stars, solar systems, galaxies, and the universe, although that's true. It's because, in keeping with what I like to make videos about, when I first learned about one of these methods, I was amazed and fascinated by it. I'll get back to that. But in order to build a framework to think about this question, we need a few concepts. The first is that of the cosmic distance ladder. What this means is we need a way to anchor unknown farther distances to known closer distances. Only very near objects such as those in our own solar system can be measured precisely. If we use different methods for different distances, methods whose ranges overlap, we can establish a distance scale, each more distant measurement dependent on the accuracy of the anchoring methods used in shorter distances on our cosmic distance ladder. This diagram illustrates the use of direct, precise radar measurement of objects in the solar system at the shorter distances, stellar parallax at greater distances, leading to the intermediate range, which is what I want to talk about today. The second concept we need is that of a standard candle. A standard candle is a way of connecting an object's known luminosity to its apparent brightness or luminosity. In other words, if an object has a known absolute magnitude or luminosity, we compare this known luminosity to the perceived brightness or apparent magnitude here on Earth. There's a mathematical formula for converting the absolute magnitude and the apparent magnitude of a star to distance. And here it is if you're interested. So now that we've defined some basic concepts, let me move in 3 quick steps to my main concern here. Distances within our solar system have been accurately measured. There's a long history in astronomy of measurement methods in the past. But today, radar gives extremely accurate measurements. The distance to the Sun is about 93 million miles, which is called 1 astronomical unit. The distance to nearby stars, ranging from a few parsecs to several hundred parsecs, can be measured using parallax. To orient yourself, the Milky Way Galaxy, our galaxy, is roughly 100,000 light years across, or 33,000 parsecs across. As seen in this diagram, a parsec is defined as the distance at which 1 astronomical unit subtends an angle of 1 arcsecond. Parsecs, 3.26 light years, tend to be the unit of measurement used by astronomers rather than light years. So parallax can only be used for stars that are relatively near us in the galaxy. In simple terms, parallax takes advantage of small differences in apparent position when distant objects are looked at from different places of observation. In this diagram, we see that if we have a star of known distance and we measure the angles created when observing that object and a more distant star of unknown distance when Earth is at opposite locations in its revolution around the Sun, for example measuring the angles in summer and winter, basic trigonometry can give us the distance. I think just being aware of that much is sufficient for this video, but if you're interested, I have linked in the description to a lovely video that illustrates this technique. So far we've talked about methods that range from distances found within our own solar system out to the stars in our section of the galaxy. This is actually a vast range of distance when you consider that the distance from Earth to the Sun is 1 astronomical unit, and the distance from Earth to the nearest star system, the Alpha Centauri system, which is about 4 light years away, a little over a parsec, but that this represents over 200,000 astronomical units in distance. What I want to talk about is measurement extending beyond this to the next rung on our cosmic distance ladder. For that, the measurement during most of the 20th century has been a class of stars called Cepheid Variables. Variables here refers to an unusual property of these stars. They pulsate rather than radiating in a steady fashion. They pulsate in brightness they pulsate in temperature, and they pulsate in size. In 1908, the astronomer Harriet Swan Leavitt, who should probably be much better known and who received relatively little recognition within her own lifetime, discovered the relationship between the luminosity of Cepheids and their period, or the interval of their variation. She found that the brighter the Cepheid, the longer its period. This allows for a fascinating calculation. You can determine the actual brightness, the absolute magnitude of a Cepheid variable by observing its period. From this, you can determine the distance to the star by comparing its actual luminosity to its apparent luminosity. You remember the formula. Wow, amazing! So there's a type of star out there that can serve as a standard candle. Observe a Cepheid variable, and its period and apparent brightness tell you its distance from Earth. Cepheids are numerous and can be observed within our galaxy and in far more distant galaxies. The North Star, Polaris, 433 light-years away, is actually a multiple star system, and one of its stars is a Cepheid. There are enough nearby Cepheids to serve as intermediate steps in our cosmic distance ladder when compared using measurements with parallax. This method works up to 13 million light-years away using telescopes on Earth, and the Hubble telescope in space has actually measured distances with Cepheid variables up to 56 million light-years away. Here's another cool fact having to do with Cepheid variables. In the early part of the 20th century, telescopes were not powerful enough to render a broad view of the universe beyond our galaxy. In fact, the prevalent view was that our galaxy represented the entire universe. Cepheid variables were actually the key to understanding that ours was but one galaxy of many galaxies. When in the 1920s, Edwin Hubble found a Cepheid within the Andromeda Galaxy, and its distance measured showed that the Andromeda Galaxy was far more distant than had been thought, and in fact could not be within our own galaxy. It's pretty cool. There are measuring methods for distances far greater than that which can be measured using Cepheid variables, but that's a topic for another day. The distances to distant galaxies using Cepheids are used to anchor another rung in the cosmic distance ladder, allowing interpretation of other methods used to measure even greater distances. I ask myself, what is it about Cepheid variables that so grabbed my attention when I first learned about them and made me want to tell you about them? The idea that we can have knowledge of something so far away, so seemingly unmeasurable, feels almost magical. It seems to get around the limitations we usually ascribe to distance phenomena in the common sense reality of tables and chairs. They are by definition almost too far away to know much about their distance just by looking at them. Of course that turns out not to be true. It's science, it's rational, it's supported by 100 years of careful observations, and it behaves according to clear mathematical formulas. But there's a sharp and breathtaking contrast between reality and expectation here. In this phenomenon, as in much of modern physics, we confront one of the strange and wonderful curiosities of the universe. I can't be the only one who marvels at the way this fascinating stellar phenomenon, this unexpected new feature of the universe, becomes a tool to measure and understand that universe. Be sure to subscribe. You can follow my Instagram, and thanks a lot for watching.